Okay, students, so welcome to Dr. Heather Maths classes. So now we will start circle, that is chapter number 10 of your book. So once again, before going to the exercise, we will try to understand the difference between the secant and tangent. So what is the difference between the secant and tangent? Tangent is a line which touch a circle at one point. Tangent is a line which touch a circle at one point, while so it is tangent. And secant is a line which intersect the circle at 2 points. So this is the major difference between tangent and secant. Tangent is a line which touch a circle at one point, and secant is a line which intersect the circle at 2 points. Now see, if in a circle is given, so a circle have how many tangents? So a circle have infinitely many tangents. Why? This is one tangent, this is another tangent, this is another tangent, this is another tangent, right? So this is another tangent. So we can draw infinitely many tangents on a circle, right? On a circle, we can draw infinitely many tangents, or in short, we can say that a circle has infinitely many tangents, right? If suppose in the question asks a circle has how many tangents, then we can write our answer is a circle have infinitely many tangents. But from a given point, if a point is given on a circle, so we can draw only and only one tangent, only and only one tangent we can draw from a given point on the circle, right? So these are the introduction and concepts. Now, first we will start with the theorem, and the theorem was very first theorem, and the statement of the theorem is the tangent at any point, the tangent at any point, the tangent at any point of a circle is perpendicular is perpendicular to the radius through the point of contact. This is the statement of the theorem, right? Means what is given? In a circle center O radius R, say this AB is tangent and this P is point of contact, then we have to prove that this OP is perpendicular to AB, right? So first we will write given. What is given? In a COR. What does it mean? In a circle with center O and radius R, AB is tangent and P is point of contact. Then to prove OP is perpendicular to AB. This we have to prove. Now come to the proof. Okay. So for the proof, mark a point Q on AB and join AQ which intersect the circle, say at point M. Okay, or we can write in the construction portion. A construction, mark a point Q on AB and join OQ which intersect the circle at M. Now we are coming to proof. Okay. So OQ can be written as OM plus MQ, and C, OP and OM both are radii. So in place of OM can we write OP. So this is OP plus MQ. Why? Because since OP is equals to OQ, both are radii. Okay. So this implies that OQ is greater than the radius OP. Am I right? OQ is greater than the radius because OP is the radius and now MQ is added. So it means this portion, this OQ is greater than radius OP. Similarly, if we mark any points on this point, on this line AB, except the point P, and we will join it from the point to the point, it will be greater than the radius. So here we will write similarly for all those points, those points which lies on AB except P or other than P is greater than radius. Okay, is greater than radius. So it means that this OP is the shortest distance. OP is the smallest side. And as we read in the 9th class, previous class, on a line segment, the line joining from the given point will be perpendicular when it will be shortest. So we can say that OP is perpendicular to AB, and this is the proof of this theorem, right? Any doubt? Now once again I am repeating, just see. This OQ can be written as OM plus MQ, and in place of OM I have written OP plus MQ. Why? Because OM and OP both are radii. Okay, OP or OM both are radii. Both are radii. So in place of OM I have written OP, and OP is the radius. So OQ is greater than the radius OP. So similarly for all those points, if we put point here P or here point, except this point P, okay, and if you will join, then this will, all the line segment will be greater than the radius. So hence AP is the smallest side. So OP is perpendicular to AB, and hence it is proved. Now come to exercise. With this concept, come to exercise 10.1. So the exercise 10.1, the very first question you see, I will solve it verbally. How many tangents can a circle have? How many tangents a circle have? Infinitely many tangents. Infinitely many tangents. Okay, infinitely many tangents. Now question number 2, first part, there are the fill in the blanks. A tangent to a circle intersect in it how many point? That is 1 point. Okay, 1 point. Second, a line intersecting circle in 2 point is called a secant. Okay, here it will be secant. And the third part is a circle can have how many parallel tangents at most? At most means this is and this are at most 2 parallel tangents. So we will write here at most 2 parallel tangents. 2 parallel tangents at the most. And the common point of the tangent to a circle to the circle is called, this point is called point of contact. This is point of contact. Okay, this is called point of contact. And third question, question number 3. And the question says the tangent PQ at point P of circle of radius 5 centimeter meet a line through center O at point Q so that OQ is 12 centimeter. Find the length PQ. Okay, find the length PQ. So a tangent PQ, draw a figure first, then it will be clear. A tangent PQ and circle of the center is given O. This is O. A tangent PQ and this is P and this is Q. At the point Q so that OQ is equals to 12 centimeter. This is given 12 centimeter. Right? Then we have to find the length. What will be the tangent length? PQ. Okay. And the radius OP is given 5 centimeter. This is given 5 centimeter. Okay. And we have to find PQ. Okay. So since QP is tangent and OP is radius, so as per the theorem, angle OPQ is equals to 90 degree. Okay, and now in right triangle OPQ, apply the Pythagoras theorem. Okay, QP square is equals to OQ square minus OP square. So this is 12 square minus 5 square. So 144 minus 25. So 14 minus 5, 919. So therefore OP is equals to root over of 119. So your options are given. A is 12, B is 13, C is 8.5 and D is 119. So the correct option is D. Okay. Now the next question is question number 4. The fourth question, the question number 4. And the question number 4 is draw a circle and 2 lines parallel to a given line such that one is tangent and the other a secant to a circle. Means what you have to do, that is the case of construction, but anyhow, let me explain. Suppose this is a circle and mark and a line is given. Suppose this line is given. And with this given line, we have to draw one tangent and another one is secant. So what we have to do, keep your pencil here and mark an arc on this line such that intersect at 2 points, and from here and here mark another arc and join it. So in this way we got a point of intersect the circle. This point we got, and this point Draw an angle of 90 degree. Okay, draw an angle of 90 degree. So this is the tangent. This is the tangent. And at this point, at the center, draw another angle of first arc is of 60 degree, second work 20, and point of intersection 90, and draw another line. Now it is secant. So in this way, we will simplify this question. Actually, it is a case of construction. Okay, so this is all about your exercise 10.1. Now I am coming to the next very important theorem of your and this is the very important theorem for your board point of view, and the statement is the length of tangents drawn from external point to a circle are equal. The length of tangents drawn from an external point are equal in length. This is the statement of the theorem. The length of tangents drawn from external point to a circle are equal. External point to a circle are equal to a circle are equal. Okay, very simple theorem, very easy theorem. First, draw the figure. In a circle center O with radius R, suppose P is an external point and PA and PB are two tangents, and we have to prove that PA is equals to PB, right? So first of all, we will write given in a circle center O with radius R, PA and PB are tangents. Then to prove PA is equals to PB. Okay. Now some construction is required here. So construction, what we will do? We will join from the center to the point of contact. Okay. And O to P. So join OA, OB and OP. Okay. Now come to proof. Since PA is tangent and OA is radius, so therefore angle OAP is equals to 90 degree. Similarly, angle OBP is also 90 degree. This is 90 degree and this is 90 degree. Now, in triangles OAP and triangle OBP, side OA is equals to OB. Why? They are radii. Okay, we will do the three pairs of matching. And OP is equals to OP. This is common. And angle OAP is equals to angle OBP is equals to 90 degree, proved above. Okay, proved above. So therefore triangle OAP is congruent to triangle OBP by which rule? By RHS, right hypotenuse. This is right hypotenuse and side. So by CPCT, congruent parts of congruent triangle, by CPCT, PA is equals to PB, and this is the proof of your theorem. Got it? Very simple theorem. Only these are the two theorems. Okay. Now we will move to the exercise 10.2, and in your example number 2 and example number 3 are very important question for your examination point of view, so that we will discuss after completing this exercise 10.2. okay, so now we are going to exercise 10.3.